My next discussion topic now will be going on in this chapter to talk about molecular ionic and net ionic equations for these different types of reactions. Particularly, we'll begin with precipitation reactions, and gradually we'll go on beyond this to cover the rest of this topic with solubility rules. But this first recording will be a shorter introduction to writing molecular ionic and net ionic equations. All right, to talk about these net ionic equations, we have to think about the ways these are represented with chemical equations and what's the difference in how we do them. First kind of reaction equation that we've encountered in general so far is what we call a molecular equation. In this type of format, all the substances involved in the reactions are written as though they were actually molecules with complete formulas. And so we write the lead nitrate and the potassium iodide as if they were actually side by side, when in fact aqueous ions are not exactly that way, but we're writing them as though they are molecules. And the first product here is potassium nitrate, which is again also aqueous, but as if they were molecules. We call this a molecular equation. Now, noting from previous information that certain things are going to be strong electrolytes and certain things are going to be precipitates. I haven't given you the rules for them yet. Then we will recognize that the lead iodide has to become a precipitate in this example and is listed as solid. The other three things are listed as aqueous because in fact they are aqueous ions and they are strong electrolytes. But the molecular equation lists all species of the reaction as though they were molecules. The ionic equation is the next type, and all of the strong electrolytes are going to be written as ions. So the strong electrolytes were the lead nitrate, the potassium iodide, and the potassium nitrate. And so we will list them in the ionic equation, which is this version in the middle, as their specific separated ions. These are very tedious to write, and you have to be paying attention to charges and phases to get them correct. And it tends to be annoying, but just think about it for a little bit. So with the lead nitrate, we're going to write the electrolyte separated as the ions in which it would be found in the solution. So you have lead 2 ions that are aqueous, and then you have 2 nitrate ions that are also aqueous. So that's the part that represents the lead nitrate when you're writing the ionic equation. The potassium iodide, there's 2 of them in your balanced equation. And so you should have 2 potassium ions and 2 iodide ions when they've separated, because this is all going to still be a balanced equation when we're finished. The products are shown on the next line. The potassium nitrate, again, has a 2 in front of it, so make sure that you haven't overlooked your balanced equation, and there should still be 2 potassium ions and 2 nitrate ions formed from this potassium nitrate that is in fact aqueous. Then the lead iodide at the end is ignored in this ionic equation, or it's unchanged. That's a better way of saying it. It's unchanged. You don't do anything with it because it is a solid. Leave it the way we saw it in the molecular equation. So that's the second type of way of writing an equation. Then we need to acknowledge the fact that there are certain things in these equations that feel a bit redundant or inconsequential, perhaps. They are described as spectator ions. The spectator ions are those species in the mixture which undergo absolutely no actual change during the reaction and will show up on both sides of the reaction arrow. In this example with the lead nitrate and potassium iodide, if you were paying attention as we were putting it all together, you perhaps noticed that there was nitrate in 2 places in this example. On one was a reactant and one was a product. In other words, it shows up exactly the same in the product as it was to begin with. It hasn't changed. And the potassium ions the same way. There's 2 potassium ions that are aqueous to begin with and 2 potassium ions that are aqueous as the product. So all of those things are spectator ions in this reaction. They have no chemical change in this process. So what do we do with these? Well, then there's yet another type of reaction representation that we call a net ionic equation. In this case, we only include the ions that undergo a change. Notice that we have 2 aqueous ions, the lead 2 ion and the iodide ions combining to make a solid. And so the only things remaining are, this is what you get after you omit the spectator ions. Omit spectator ions. This form seems a lot more streamlined because it is. It's omitting things that have no part in the actual process. They're just there to bring in their respective counterions, the other cation or anion, but they don't chemically change. And so this diagram on the right, again, represents the lead iodide, which has a nice yellow color. That, in a general sense, is what we need to do to represent net ionic equations. So you start with a molecular equation to write out the whole thing and make sure it's balanced. Molecular equations show everything as though they're molecules. Then you come up with an ionic equation where you separate all the strong electrolytes into their component ions. Then you take a step of identifying the spectator ions and note where they are so that you don't have to include them. And the last piece then is to write a net ionic. So the net change is represented here in the net ionic equation, leaving out the parts that have no change. All right, that was a short recording on purpose. We will talk more about these examples with more examples in the next section. I hope it helps you on your homework. Ask more questions, and I'll see you in class.